All right, we're in unit number 6, working through energy. In this particular video, we're going to work through conservation of energy and then switch over and work through example number 3. In a previous video, we talked about this whole idea of conservation of energy as being a very, very powerful law in all of science. Well, you're going to start to see the power of that law in these next couple of videos. Let me first define conservation of mechanical energy, run through an example, and then we'll go to example number, I think it's example number 3. So let's start it out. So conservation of mechanical energy. The total energy remains constant for an isolated system in which only conservative forces are exerted. Alright, so what does that mean? It means the mechanical energy that you have at the beginning is going to equal the mechanical energy that you have at the end. And I'll run through an example in just a bit with that. So forms of energy associated with mechanical energy. We've talked about this before. Kinetic energy, gravitational potential energy, spring potential energy, or you could say elastic potential energy, and rotational kinetic energy. So those are the forms that we want to keep in mind when we run through those. All right, I've got a little cartoon down below. We're going to use the cartoon to answer this next question on the next page. You've seen this cartoon once before already, so I'm not going to spend a lot of time going through the cartoon, but let me at least read it for you. It says, let's see, so this guy is on the top of this swimming pool, on the top of this diving board. He's going to dive into this pool, and he's starting to run the numbers. So let's see. 50 feet up, acceleration of gravity is 32.2 feet per second squared, which means I'll be going 87 miles an hour when I hit the pool. Kind of scary. So there are times when being a whiz at physics can be a definite drawback. Well, we're going to use that cartoon to answer example number 3 on the next page. So we're on page 9 of your notes, and let me read the first question to you. And you've seen this question before. We did it in another unit. So use conservation of energy to determine if the author, who's going to be 4.8 slugs, of the prior cartoon is correct. Remember, this is the same cartoon from page 5 of unit number 2, problem set question number 15. So you've answered this question, but we use the big 3 to answer it. And in this particular question, we're going to use, I got to sneeze. In this particular question, we're going to use conservation of energy to answer this question. And at first you're going to say, hey, I really like the big 3, and I would prefer to use the big 3. Well, you're going to find out that I think once you get used to using conservation of energy, you're going to find out it's going to be much, much easier and much more powerful than the big 3. Big 3 is nice, but conservation of energy is going to be even nicer. So let's run through this. Let's get started. When we use conservation of energy, our starting point is going to be right here. Energy at the beginning, E sub O, and energy at the end, energy at the final, are going to be the same. And so we're going to use that as our starting point. So at the beginning, we want to list all the forms of energy that we have. So let me flip this over, go back to the cartoon. Here's our forms of energy. So what forms of energy do I have at the top? Well, I have gravitational potential energy because I'm above the water. We're assuming the reference point is going to be the water. We're not in motion, so we don't have kinetic. He's not, and I know there's a diving board here, so you could maybe think about elastic potential energy, but let's just assume that it's a platform and there's no spring to it. So there's no elastic potential energy, and we're assuming he does like a pencil dive, so we're not going to be rotating. So the only form of energy we have at the top is gravitational potential energy. So we're going to go back over here. We're going to put down gravitational potential energy. All right, the next one. We want to know what forms of energy we have at the end when he strikes the water. Well, he's in motion. So he'll have kinetic energy. Since he'll be on the reference point, he won't have any gravitational. We're assuming he's not rotating. We're assuming he's not going to have any kinetic or elastic potential energy down there as well. So he has only kinetic at the end. So we start with gravitational, and all of our gravitational gets transformed into kinetic energy. Next step is to go ahead and substitute equations. So I know the equation for gravitational potential energy is going to be mgh, and the equation for kinetic energy is 1/2 mv squared. All right, now the next part. we want to know how fast he's going to be moving when he hits the ground. Uh, the guy in the cartoon said 87 miles an hour, and I'm not sure if you remember this, but that's not right. So he did a wrong calculation. So let's go ahead and solve this. You notice that the mass is going to cancel out. Now that's interesting. When the mass cancels out, that's, there's a lot of meaning. That means the mass of the guy is irrelevant to the speed with which he's going to strike the ground. And we've actually talked about that this year. We've said that if you drop two objects, the speed with which it hits the ground is not dependent upon the mass. You can drop any two objects as long as air friction is not a big concern. They'll hit the ground at the same time. And that's what that's saying. There's a lot loaded. There's a lot of science loaded in just the fact that you cancel those masses out. There's a lot of science there. Now let's solve for v. So v is equal to plus or minus, because I got to take the square root, plus or minus 2gh. Now I'm just kind of thinking here a little bit. That sure does look familiar. If I go back to the big 3, see, I can't even do this in my head now. 2AD, there it is. Initial velocity 0. Look at this. VF is equal to this plus or minus the square root of 2AD. This guy and this guy are basically the same. Yeah, A, acceleration, G, it's acceleration in gravity. H and D are basically the same thing. So whether you use the big 3 or whether you use conservation of energy, you're going to get not only the same answer, but sometimes the formulas are going to start to look alike. Now I know what you're thinking. Boy, this is a lot easier using this than conservation of energy. Let me go back to what I said earlier. At first, you might think that the big 3 is going to be easier, but trust me on this. Conservation of energy is going to be better in the end. All right, let's just go ahead and plug in the rest of the numbers here. So we got plus or minus the square root of 2 times, see, we're going to do 32 feet per second squared. And then a height, what was the height that he jumped off at here? We had 50 feet up. So let's put 50 into there. And then v is equal to, and then let's plug it all in. So we're going to do 2 times 32 times 50. And then we need to take the square root. That doesn't make sense. Let's try that again. So 2 times 32 times 50, get that answer. Now let's take the square root. Let's see if they let me do this. Hey, there it is. 50.56. So did I say that right? I said that wrong. 56.56. So 56.56, and that'll be, let's see, feet per second. Now, the guy did his calculations in miles per hour, so we have to do the conversion. I'm going to do the conversion up here. So we got basically 56 miles per hour. I did that wrong. Try to go fast here. Feet per second. Let me slow down. There's 5,280 feet in every mile, and then 3,600 seconds in every hour. Now let's go ahead and finish that off. So I got 56 times 3,600 divided by 5,280, and we get 38 miles per hour, which is not even close to what he calculated, so he was wrong. But the more important part is the fact that we didn't need the big 3. We used conservation of energy to get the answer. That's a big concept. All right, so next question says, with what average force in pounds does the water push up on the diver as he comes to rest just before he hits the bottom of the pool 12 feet below the surface of the water? All right, there's a lot there, and I guess I want to start you off with this. We're looking for force. Conservation of energy does not have forces in it. And so a tip-off when you're working through these, if they ask you for force, probably not going to use conservation of energy because we don't have force show up in our energy formulas. So we're going to have to kind of go back to the big three. So I know you're cheering, yes, the big three. Um, and then we'll use Newton's second law to actually get our answer for this particular problem. So let's go ahead and set up the big three, and then see where it leads us. So we've got D, VO, VF, A, and T. This is while he's coming to rest in the water. So here's the bottom of the pool. Here's the water at the top, and he's going to come to rest at the bottom. So we need the acceleration. I'll show you why here in just a bit. We need the acceleration, so we need three of the other four to be able to get the acceleration. Well, I know the distance because that's negative 12 feet. That's what they said right here. He comes to rest in the bottom, so that's going to be 12 feet per second. He comes to rest just as he strikes the bottom. His initial velocity is really the velocity at the beginning. Or, let's see, I didn't say that very well. His initial velocity of the second part is really the final velocity of the first part. So while he was coming and accelerating in the air, he struck the water at 56 feet per second. Well, then that means that's the end. Let's see, that's the final velocity of the first part, which becomes the initial velocity of the second part. So I can put this down as 56.56 feet per second. All right, I'm going to use the big three to get the acceleration. So I'll use VF squared equals VO squared plus 2AD. There's that. Solve for A. A is equal to negative VO squared over 2D. Substitute negative, negative. This is going negative because he's going down. 56.6 feet per second, all squared, divided by 2, divided by 12. And there it is. All right, so let's plug this into the calculator and see what we get. So I got 56.6. Let's see, I'm just going to do the signs in my head real quick. This negative is going to get squared, so he's gone. But this negative and this negative are going to be gone as well. So my answer is going to be positive. So I'm not going to worry about the signs when I do all these. So 56, I'm going to square that. Then I'm going to divide by 2 and then divide by 12. Make sure and throw in the divide sign. Not all calculators interpret that correctly if you're not careful. So that's that's going to be 133, and that'll be feet per second squared. All right, now we want to know the force of the water acting on him. So let's go ahead and run a free body diagram. So while he's coming to rest in the water, see, he still has weight, so gravity's still pulling on him, but the water's pushing up on him as well. So let me put maybe like H2O there. So I've got two forces acting on him while he's coming to rest. So when I go back and do Newton's second law, I've got the force of water, I would use W, but I got W down here, minus the weight is equal to MAY. Now, I am accelerating, so the right-hand side of this equation is not going to be 0 because I'm coming to rest. So, and what do I want? I want the force of the water, so that's going to be this guy. So I'm going to go F H2O is equal to W plus MAY. Now let's just see what I've got and see if I've got enough information to solve this one. I have the acceleration, just figure that out. I have the mass of the guy, that was from way up here, 4.8 slugs. My problem is I don't have his weight. So I'm going to go, boy, I'm running out of room. I'm going to have to use this part down here. So I'm going to have to go mg plus MAY. And now I have enough information. His mass is going to be 4.8 slugs. G, since I'm using slugs, I got to use feet. So it's 32 feet per second squared plus 4.8 slugs times his acceleration, which is right here, 133 feet per second squared. And then I'll plug all that in. So here goes. So I've got 4.8 slugs times 32, get that answer. And then 4.8 times 133, get that answer. So I'm going to add that previous one. So if I add this to this, the 153.6, I get the final answer. So this is going to be 792, and that'll be pounds. Since I'm using feet and slugs and seconds, my answer is in pounds. So on average, there's 792 pounds of force pushing on him by the water to bring him to rest. And there it is. On the next video, we'll do example number 4.